Hi, this FAQ was developed as part of the Linear and Switching Circuits unit of the Electronics Combined framework at Bournemouth University. The objective is for you to understand and to be able to explain the basic construction and operation of a Jfet transistor. The material should help you with the analysis and design of FET circuits. Jfets, or junction field effect transistors, come in P and N channel varieties. Let's start with the N channel device. The channel is simply a block of N-type semiconductor with a source terminal at one end and a drain terminal at the other. Applying a positive voltage to the drain end will attract the free electrons in the channel, and they'll flow from the source to the drain, giving a conventional current direction from the drain to the source. And increasing the voltage on the drain will increase the drain current. The junction part of the Jfet is formed by the p-type gate terminal. This creates a p-n junction between the gate and the channel. The junction is kept reverse biased in normal transistor operation. That is, a negative voltage is applied to the gate, reinforcing the potential barrier at the junction and repelling the electrons from the channel. The reverse bias junction will form a depletion layer, and that will extend into the channel. The gate is more heavily doped than the channel in order to increase this effect. Increasing the voltage on the gate will increase the size of the depletion layer. At some point, the pinch-off voltage, Vp, generally somewhere between -1 and -4 volts, the depletion layer will extend across the whole width of the channel. Now, with no voltage on the drain, the depletion layer is evenly spaced around the gate. However, the drain is normally kept positive to draw a drain current. And as the drain current flows through the channel, it will set up a potential gradient which increases linearly from the source through to the drain. Now the reverse bias between the gate and the channel will be higher at the drain end of the channel than at the source end, and the depletion layer will be correspondingly larger towards the drain. When the drain voltage is increased, the depletion layer grows and will pinch off the channel at the drain end. However, it can't entirely close the channel because the reverse bias is itself dependent on the channel potential gradient set up by the drain current flowing through it. What will happen is that the pinch-off will simply prevent an increasing drain voltage from producing any further rise in drain current. It effectively insulates the drain current from any change in the drain voltage. Now, increasing or reducing the negative gate bias will expand or contract the depletion layer and change the part of the channel which can give rise to the drain current. The overall effect is that a small change in the gate voltage will produce a large change in the drain current. This slide shows some comparisons between the FET and the bipolar junction transistor, the BJT. The BJT is a current control device whereby the output collector current is controlled by the base current input. The Jfet is a voltage control device in which the output current is directly controlled by the applied gate voltage. The BJT has a relatively low input impedance in the hundreds to thousands of ohms range. The Jfet has a very high input impedance in the megohms range. The BJT is a bipolar device with two types of charge carriers, holes and electrons. The Jfet is a much simpler unipolar device with one type of charge carrier, electrons for N-channel devices and holes in the case of P-channel devices. In addition, the FET is much simpler to fabricate, particularly in complementary CMOS form, which can be made with very high component density and low power consumption. This slide shows the relationship between the output drain voltage and the output drain current. There are two main regions of operation here, the ohmic and saturation regions. The ohmic region is where the drain voltage is less than a volt or so. The channel isn't pinched off, and an increase in drain voltage will produce a more or less linear increase in drain current. So the channel acts like an ohmic resistance. However, the transistor is mostly used in the saturation region. Here the channel is pinched off at the drain end by the potential difference between the negative gate voltage and the positive potential gradient in the channel. The drain voltage has negligible effect on the drain current in this region. The graph is essentially, although not quite, flat, but the gate voltage is in full control, with the output drain current increasing as reverse bias on the gate reduces. With zero gate voltage, increasing the drain voltage will eventually pinch off the channel on its own. The drain current is then the maximum possible, or saturation drain current, IDSS. This slide shows the relationship of the output drain current to the input gate voltage. That is, it shows the gain of the device, or rather its transconductance, as we're talking here of a current output with the voltage input. Provided the FET is in its saturation region, we needn't worry about the drain voltage, as it won't affect the output very much, but the gate will. At the one extreme of this rather nonlinear square law characteristic, the gate voltage provides sufficient reverse bias to cause pinch-off at -Vp when there is no drain current, that is, without any help from the potential gradient in the channel. At the other extreme, with zero gate voltage, it's the channel potential which causes pinch-off. The drain current is then at its maximum possible, or saturation drain current, IDSS. These two parameters are important in characterizing the Jfet performance. As the characteristic is nonlinear, we can represent the small signal gain, or conductance Gm, as the slope of the curve at the appropriate circuit DC operating point. Now, here are some problems for you to check out your knowledge. Please remember to refer to the list of facts for further assistance. Thank you.